Okay. Yep, I've got the message confirming it. Okay, so welcome everybody to the very first lecture in our season, which will extend through the winter into the beginning of next spring and summer. And we've got an excellent start to the lecture season, I think. I'm delighted to welcome Catherine Heymans, Professor of Astrophysics at the University of Edinburgh and Director of the GCCL Institute at the University of Bochum, Germany. She specialises in observing the dark side of our universe, using deep sky observations to test whether we need to go beyond Einstein with our current theory of gravity. Now, amongst her many accolades, the most recent one, or one of the most recent ones, is that she became Astronomer Royal for Scotland. Now, the previous Astronomer Royal for Scotland, John Brown, had a long and close association with this society, and I hope we can continue such a connection, even if it is from Edinburgh. After all, on universal scales, Edinburgh is Glasgow to a very good approximation. Catherine, can you please tell us about observing the dark universe?
Oh, thank you very much, Andrew. And yes, no, you're quite right. Edinburgh is Glasgow. It is a great honour for me to join you all this evening to follow in the very fine footsteps of my predecessor, the fabulous John Brown. It's a great honour to be the 11th Astronomer Royal for Scotland, and one of my jobs, everyone keeps asking me what is the job of the Astronomer Royal for Scotland, and I sort of look back at what the fabulous John Brown used to do, and I'm afraid I can't do magic tricks. Unfortunately, that's not in my repertoire. But you know, John was absolutely fantastic at both being really amazing astrophysicists, but also supporting the amateur astronomy groups across Scotland. So I am looking forward to following in his footsteps there. The Astronomy Society of Edinburgh have taken me under their belt. They have been training me in amateur astronomy because I just go out and use the really big kit. So I'll show you some pictures of the telescopes I use later, but you just type things into a computer and it points. So it's a whole new world for me, amateur astronomy, but I'm absolutely loving it. And I hope that when we get back to in person, I can actually come through to Glasgow for one of your actual astronomy nights and actually get to meet you all in person. But without further ado, let me tell you about my research, and let's see if the power of Zoom is going to allow me to share my screen with you this evening. Hopefully you can see that. So is that coming through for you all?
Looks great.
Wonderful. Okay, so in these events, it's a bit of therapeutic, it's a bit of therapy for me, these events. So I'll start off by sharing with you one of my most challenging moments as a parent, because you know, a lot of us parents and grandparents have been going through challenging times recently. Homeschool, that was a big challenge, but this particular challenging moment as a parent went back to, gosh, 2012. Now, this blobby map that you can see here, to you might just look like a load of blobs, but to me, this represents 7 years of my life. What I'm showing you here is, at that time, the first wide-scale image of dark matter in our universe. I was at a conference with lots and lots of eminent astronomers. I was just a postdoctoral researcher at the time, but there'd been a bit of a childcare crisis, so I had to bring my 4-year-old with me, and he was really ill and very grumpy on the front row. I mean, I don't know what I was thinking bringing him with me, but anyway, he was there, sat on the front row, and I was just getting to the point. I'd gone through all of the details of how I created this map of invisible dark matter, and I was just getting to the point where I was going to unveil this gorgeous map when my son decided to jump up and shout out, "My mummy doesn't understand what she's talking about." Oh dear, very embarrassing, very embarrassing. Now, the reason why I continue to share this story with people like you. Much to my son's disgust, he's now 12 and actually sat on the other side of that wall saying, please, Mum, don't tell that story again. The reason why I share it is because at the time he was being very astute, because we don't know what we're talking about. As scientists, we don't know what we're talking about when we're talking about the dark side of our universe. And what I want to do tonight is share with you as much as we do know, and hopefully get you excited about what this stuff could possibly be, and why we're so passionate to try and understand it. So here we go. This is the absolutely gorgeous Hubble Deep Field. It's an absolutely iconic image for 10 whole days. In fact, actually, this is the extreme deep field. So this is 22 days. The Hubble Space Telescope stared at this tiny patch of sky. The sky you can see here is 1/24 millionth of the entire sky. So it's a tiny patch of sky, but look, it's teeming with galaxies of all different shapes and sizes. And you know, I just love looking at this image. It's absolutely gorgeous. The most distant galaxy in this image, its light has taken 13 billion years to reach us. I mean, that's just one of the very, very tiny fuzzy dots at the back. It's an absolutely gorgeous image, and it tells us so much about galaxies. But what you're looking at here, all of the stuff we can see, the stuff these stars and galaxies are made up of, the stuff that you and I are made up of, the Earth, the Moon, anything a particle physicist can explain, that accounts for less than 5% of our universe. Less than 5%. And if our theories are right, the rest of our universe is dark. Now, there are two entities on the dark side. One of them is called dark matter. Now, dark matter is the strong gravitational force in our universe. It likes to pull things together. It's the thing that dictates where and when galaxies form in our universe. And I kind of like to think of dark matter as kind of like a nice tidy child, maybe sort of sat in a room, putting a nice jigsaw piece together, putting all the pieces together, bringing it together, making a nice tidy universe. Unfortunately, dark matter isn't on its own, though, on the dark side, because there is another entity called dark energy. Now, what dark energy appears to be doing is it appears to be causing the expansion of our universe to accelerate. We've known since Edwin Hubble first measured distances to galaxies that those galaxies were moving away from us. But what we learned recently was that expansion was getting faster and faster. I often think of dark energy as kind of the evil sibling in this dark pair. You've got dark matter nicely putting everything together, that nice jigsaw piece, all making a tidy universe. And dark energy comes along, just throws everything apart again. It's causing everything to just move away from each other at an accelerated rate. These are the two subjects that we're going to be focusing on this evening. If you remember nothing else, if your internet connection dies, the reason why we care, the reason why this is really interesting, these two dark entities, is we can't explain them. The fundamental physics that I teach at the University of Edinburgh and people teach across the entire world, the physics that we teach cannot explain these two dark entities. We need some new physics in order to explain them. So what I'm going to share with you is the observations that we infer that these two things have to exist. Let's start off with a good level of scale, though, just to make sure we are all exactly on the same page here. So we are, of course, on planet Earth, orbiting our sun, which is just one star in the Milky Way galaxy. For every human being on planet Earth, you get to choose about 3 or 4 stars in the Milky Way galaxy. And everyone's going to pick the bright ones. So you guys, as you know what you're doing with amateur astronomy, you get to pick some of the fainter ones, but everyone gets about 3 or 4 stars each. That just tells you just how many stars there are in our own Milky Way galaxy. And we're going to pause at this point in our journey up in scale, because I'm going to give you our first piece of evidence for dark matter. So this is not an image of our own Milky Way galaxy. We haven't been outside our own galaxy, but this is a galaxy that looks not so dissimilar from our Milky Way galaxy. It's a spiral disk. Now, what we can do with this galaxy is that we know roughly how much stars weigh, because we know how much our sun weighs, and our sun's pretty typical. So we know roughly how much stars weigh, and we can measure how fast the stars are moving around in the galaxy. So you can look at how their speed as they orbit the center. Now, what I want you to do now is cast your mind back to when you were young and you could embrace your inner cowgirl or your inner cowboy. You would swing something around your head, okay? And you must have done that at some point in your life. It's very liberating. So you're holding on to swing something around your head. The faster you swing something, the tighter you have to hold on to it. Now, we've got stars moving around in this galaxy, and they are moving quite quickly. Now, those stars are not attached to the galaxy. There isn't a piece of string keeping them hold on. What's keeping all of those stars bound in the galaxy going around and around is gravity. Now, you can count how many stars there are. We know roughly how much each star weighs. So we know how much gravity there has to be in this galaxy from just the stuff we can see, and there's simply not enough. It's like nowhere near enough. A typical galaxy, there is 50 times too little matter from just the stuff you can see. So we infer that that means there must be some invisible extra stuff there that doesn't emit or absorb light, otherwise we'd see it. But it's there, lending its weight, lending its gravity to keep the stars bound. If we didn't have these dark matter around our own Milky Way galaxy and all the other ones that have been looked at, those stars would simply fly out into space. They're just moving too quickly. So that's our first piece of evidence for dark matter. And at this point, I'm going to take a little poll. Now, we are going to have to do this through the power of Zoom, and I'm wanting to see this evening what your thoughts are already on this idea of dark matter. So you've got two choices in Zoom. We're going to be using the reaction button at the bottom. So on the bottom of your screen, next to the chat button, there should be a reaction button, and you're going to have two options. You can do the reaction emoji for if you think what I've told you so far is utter nonsense, that I've probably got my sums wrong. So I've said there that I need to count up the stars to calculate the gravity. There's not enough there, so I'm going to infer there's some other stuff there. And if your reaction to that is utter nonsense, then in a second I'm going to ask you to press that reaction button. All right. But maybe you're quite happy with this idea. You're quite happy that there's this need for a new particle, and this new particle is going to have to hardly interact with the stuff we're made up of, because if it interacts with the stuff we're made of, we would have already found it. So it's some new type of particle that hardly reacts, and hoping we're going to find one soon. For that, you're going to need this reaction. Okay, so for the utter nonsense, you're looking for the one, and this one is for the new type of particle. Now, at this point, I'm going to stop my screen share so I can actually see. Hang on a moment. Here we go. Let me stop my screen share. Right, everybody, I'm going to put up my gallery. So hopefully you've all found the reaction button at the bottom of your screen. It's like a little smiley face with a plus. All right, so we've got some thumbs up already. And if your thumbs up was, I'm happy with what Catherine's saying already. Andrew's just laughing. He's just crying with laughter. Thumbs up if you're happy. You can also do it in video form as well. If you can't find the reaction button, you can either give me a thumbs up or a oh, John's unsure. We've got some dissenters in the audience. We've got some dissenters, some thumbs up. It's kind of 50-50. Well, 50-50 between the people who are voting. Everyone else is like, what is this mysterious button in Zoom Catherine is asking us to press? But mainly, we've got mainly thumbs up. For those of you who would have pressed the she's talking utter nonsense button, but didn't want to be rude, Oh, we've got a thumbs up on YouTube as well. Thank you very much, Laura. Thank you very much, people on YouTube as well. For those of you who would have pressed the utter nonsense button but you didn't want to because you were rude, actually, do you know what? I would have completely saluted you for doing that. Our job as scientists is to question things. That's our job. We have to question everything around us. I've told you about this galaxy and needing extra stuff for the gravity, but you know what if our model of gravity is wrong? You know, we have to question these things. That's our job as scientists. We don't believe in things. We just have our theories, and our job is to try and disprove these theories. So if Einstein's theory of gravity is right, we need dark matter around these galaxies, or I need to understand stars better. But we understand stars really well. So let me carry on. This is only my first piece of evidence. And I should name drop at this point that it was Vera Rubin, who was the astronomer who made those very first measurements. Well, not the very first, but she made the big series of measurements to really give that crystal clear evidence for the need for dark matter in and around every galaxy. If that was our only source of evidence for dark matter, you could play around with gravity. There are lots of different types of gravity models. You could get away with it somehow, but that's not our only piece of evidence. So let's go up. Let's go up in size to our local group. Andromeda is our nearest neighbour. My favourite Andromeda fact I learned yesterday was that Andromeda is 2.5 million light years away. And that means if there's a technologically advanced civilization on Andromeda looking back at us on Earth now, and if they had a telescope about the size of the Earth, so it had really amazing resolution and they could like zoom in on what was happening on planet Earth, they would see the first humanoids on planet Earth just about starting to think about walking on 2 feet. I love that. So Andromeda, even though it's our nearest neighbour, it still would take us 2.5 million years to travel there if we could travel at light speed. Our local group is gorgeous. I love our local group, but actually most galaxies live in big clusters. So you can see the hundreds of clusters, hundreds of galaxies in this cluster. So we're building up in scale again. And if you zoom out now onto really sort of universe scales, what you see is something that we call the cosmic web. You see this really webby-like structure. Now, I hope both my internet and your internet can cope with this next movie that I've got now. If it's not coping with it, do Google it on YouTube afterwards, because this is an absolutely awesome movie from the Sloan Digital Sky Survey. This is real data, people. The Sloan Digital Sky Survey is a fantastic US project where they have been mapping out the full 3-dimensional distribution of galaxies out to a couple of billion light years away. And what you can see, what I hope you can see if my Wi-Fi and your Wi-Fi are coping, is that these galaxies are not randomly distributed across our universe. Hopefully you'll be able to see sort of like kind of string-like clusters. You've got those clusters where they're all joining together, a kind of a webby-like structure. And this cosmic web-like structure is exactly what we'd expect to see if we could also see the dark matter. So what we're doing now, if the internet is working, is flying through a numerical simulation of what the universe would look like if you could see dark matter. So the bright spots here is where there's lots and lots of dark matter. And as the color scale gets cooler, that's where there's less dark matter. And you can see exactly what we see in the galaxy distribution. You get these knots where there's lots and lots of clumps of dark matter, and each of these clumps will house a different galaxy. And you also see this webby-like structure. And to form this sort of simulation, you need a special type of dark matter particle that doesn't interact with the stuff that we're made up of. All right, here's a still now, just in case none of that worked through Zoom. This is what the universe would look like if you could put on a pair of dark matter spectacles. Now, when I started my PhD, I thought, oh, well, this is all very nice. We've got these fantastic galaxy surveys. We've got this simulations of what the universe would look like, but wouldn't it be great if we could actually see the invisible, map out this dark matter? So that's exactly what I did. And to help me explain how I could see this invisible stuff, even though it was invisible, I'm going to use a video from one of my friends in Stanford. He's going to do an experiment now that anyone can do the next time they're having a romantic evening with wine glasses and candles. All right, let's see if this is going to work. So here we go.
Okay, so if I just look right through the base down here, I can see 2 images. Oh, there's 4.
All right, so what's happening here is Phil is looking through the base of his wine glass at a candle, but the light from that candle isn't traveling in a straight line between the candle and his eyes. The base of that wine glass is bending and distorting the light, and the light can travel in different directions around the base of the wine glass, so he sees multiple images of the lens, multiple images of the candle. Now, this is called lensing. It's exactly, if any of you are wearing glasses, it's how your glasses work. They bend the light to help assist your eye in its job. And what's interesting is we can do this experiment in space, except we don't have lots of wine glasses now. We have big clumps of matter.
2 again. And if I look
now, Einstein tells us that matter curves space and time. So here's a distant galaxy, and that light is traveling across the universe towards us on planet Earth. And what happens is the gravity of that big clump of matter, the yellow clump of matter in the middle, that's curving space-time, which bends the light, and so that changes the image of the galaxy that I see. And it doesn't matter whether the matter is luminous matter or dark matter. It simply doesn't matter. Oh, too many matters. Okay, so let's see. Oh, my curious. My internet has just, let's see. Yes, go away. Haha, bear with me a second. We're having a small technical problem. All right, good. Hopefully you can see that. Shout if you can't. All right, so the idea is I go and look at lots and lots of galaxies. I'm totaling about 100 million galaxies in my career now. All of those galaxies are very far away in the universe. The typical galaxy that I look at, the light has taken about 7 billion years to travel to be caught in our telescope. For 7 billion years, this light is traveling through the universe, but each time it goes past a clump of dark matter, its path gets just slightly distorted, and you see that in the yellow, orange and green lines here. So when I actually look up at the night sky, the galaxies appear to be very weakly distorted. Now, the image at the bottom is really exaggerated, so you guys wouldn't see it with your telescopes. It's a tiny sort of percent level effect. But if I measure it across enough galaxies, then I can use it to map out where the invisible dark matter is that's caused these distortions in the first place. So here's my kit. I am very lucky to co-lead a big European project at the European Southern Observatory. We use 2 telescopes. This is Paranal. We use the VST telescope, which is the little telescope on the side of the main site at the top of the image here. That's observing the sky in the optical wavebands. And we do the full range of optical colours. We also use the Vista telescope, which is the Billy No Mates at the bottom, the sight off to the side, that's the near infrared telescope, and we observed the same patch of sky with both of those telescopes. Now we have been observing since, gosh, 2012. I'm really excited to tell you that we took our absolute last observation last week. Our final observation was completed last week. So that's really exciting. After numerous COVID delays, we had to, the whole site had to be shut down during the pandemic, quite rightly so, because this is an incredibly remote site and they were very concerned about the health of their staff. But it's back open again now and working at full tilt, and it's a fantastic observatory. Okay, so here is the zoom in of the kit. This is the VST telescope that does most of our work. The top image there is the mega camera VST. At the time that this was installed in the telescope, this was the largest optical camera. It is no more, it has been surpassed since then, but it is an absolutely amazingly exquisite camera for this type of study. And everything that I'm going to show you today, it's not my work alone. This is an awesome crew of people. I think often when you think about sort of science, I think, well, certainly sort of popular culture will tell you it's full of people either like Sheldon from the Big Bang Theory or old men with Einstein hair, but it's not like that at all. This is our fantastic team. We're mainly in Scotland, England, Netherlands and Germany. This particular trip pre-pandemic, we were in the Netherlands, and I got a little bit bored one afternoon and decided that I simply had to go and see every single coloured tulip that there was. the fools came cycling with me. They got a bit bored. The bottom one, they were a bit bored. By then they were like, we've already seen a pink field, Catherine. But fantastic team of people who made all these results possible. All right, so let's recap. Here we go. This is one of our images. What are we wanting to do? We are wanting to look for this mysterious dark matter that I've told you is there because of the effect that it has on the things that we can see. The yellow dots that you can see are galaxies in a cluster, a big kind of clump of galaxies in the foreground. And what I'm going to do is look at the little blue dots that are in the background, and their light is going to be bent by the gravity of the stuff in the foreground. So just like that candle was bent by the wine glass, this clump of galaxies and the dark matter that I think must be around it is going to bend the light of those distant galaxies. Now, nobody knows what dark matter is. We don't have a good understanding of what it could be, but I'm quite convinced that if dark matter had a colour, it would be pink. Yes, there we go. This is where the dark matter is in this particular patch of sky. This is where we infer it is because of the gravitational pull, or gravitational distortion it introduces on distant galaxies. And you can see this is exactly what we predict, that the dark matter is housing these galaxies, this big clump of galaxies in the foreground. And we can do this across the whole sky. So I said, you know, at the start of my PhD, I really wanted to be able to see the invisible. Well, here's this, the band across the middle here, that's a real map of dark matter. So more advanced than the small blobby map that I showed you right at the start. So this is one of our most recent maps, bringing you up to date. The dimensions across the sky here, just imagine looking up at the night sky. It's about from your elbow to your fingertip, sort of looking up like that. And the hot spots here is where there's lots of dark matter, and the cool spots is where there's very little dark matter. And you can see it has that webby-like structure. It's not as good as the numerical simulation, but it's real. So that makes me happy. And this is our most recent maps projected across the sky on parallel. So these are some of the largest maps of this invisible dark matter. And I would be remiss at this point if I pretended that we were the only team doing this. Of course, the Europeans aren't going to be the only people doing this. The Americans are also doing it. Their telescope is bigger than ours. Yeah, lots of things in America are bigger, aren't they? The cars are bigger, the Coca-Cola is bigger, the telescope's bigger, the dark matter map's bigger as well. Oh my God, it's awesome. I'm so proud of my American cousins. This is the Dark Energy Survey. Their map is 4 times as big as ours, and it's absolutely gorgeous. You see exactly those same, that same structure across the sky. So astronomers have done it. We've been able to put on dark matter spectacles and map it out. But unfortunately, we still don't know what it is, Curtis. So then we have to turn to our particle physics cousins. Now, astronomers go to the top of mountains and they stare up into the universe to work out what's out there and what the galaxy is doing. My particle physics colleagues bury themselves deep underground, far away from anything that could contaminate them. This is underneath the South Dakota mountains, and this is where the Lux Zeppelin dark matter detector is currently based. They are trying to catch a dark matter particle. This is a schematic of what it looks like. The idea is there are all of these dark matter particles flying around. So if there's dark matter around our own galaxy, there must be also some here in the room with you. And these particles, the idea is they crash into this giant vat of xenon. And in doing so, they create a little bit of energy, and then the particle physicists can say, ah, we've caught a dark matter particle. Each time they build one of these things, they don't quite manage to find anything. So they build a bigger one, and then they build a bigger one. And what's being proposed at the moment is, you know, the biggest dark matter detector that they could possibly build with the entire world's supply of xenon. I'm kidding you not. And much to my excitement, one of the places where this might be built is Bolby Mine in Yorkshire. This makes me very happy because I really, really love the idea of the Sun newspaper with the headline on it, dark matter particle caught in Yorkshire. That would be a wonderful and a joyous thing. Until that happens, we are still going to be sitting on the fence of what this dark matter particle is. Another alternative is they might create it at CERN, so they're cranking up the energy at CERN, they're smashing particles together. It could be that some dark matter particles fall out of that. But I'm hopeful that it won't be too much longer before I will be able to tell my son that I do understand dark matter. But what we are going to talk about next is dark matter's evil sibling, dark energy. Dark energy is a bit more of a problem because whilst we have some good ideas about what dark matter is and are very good, we do very well at mapping it out and telling you where it is, dark energy is a genuine mysterious puzzle for us. So let me tell you a little bit of history about dark energy first. And to help me tell this story, I will share this lovely picture. This is a picture from the 2011 Nobel Prize ceremony in physics, which went to these three gentlemen for their discovery of dark energy. We've got Saul Perlmutter on the left. He led the big US team with the big telescope. On the right, we have Adam Rees, and in the middle, Brian Schmidt. They had the small telescope in Australia, small team. Now, let's take a moment to look at the body language in this image. Do we think these gentlemen like each other? I think I'm not sure. They're all fantastic gentlemen. Saul Perlmutter, he came up with the idea. He had the big telescope, the big team, and the idea was when stars die in a supernovae explosion, they always emit the same brightness. Okay, so take a moment to imagine that you're super rich and you've got a really massive garden. You could have one of you standing at your back porch and the other one could back away from you holding a torch. And you would be able to tell how far that person was away down your back garden by how dim their torch was. Yeah, so the further you are away, the dimmer the torch is going to go. So supernovae are like that. They're all, when they go bang, they all emit the same amount of light. And so you can measure how bright they are, and then you can work out how far they are away. So they're a way of kind of measuring distances in our universe. You can also measure how fast they're moving away from us from something called their redshift. It's like the Doppler effect, you know, when an ambulance goes past you. No. You can measure how fast things are moving away from us. So Saul Perlmutter came up with this idea. had the amazing team. He was very conservative though. He was wanting to get a lot of supernovae together before he was convinced of his results. Plucky Australian team though, small telescope, 9 supernovae, published the results. And their result was mind-blowing, because not only did they confirm Hubble's original measurement that the universe was expanding, but they found something very surprising, that the further the supernovae were away from us, the faster they were moving away from us. That expansion was accelerating. And I think if it had just been the Schmidt-Rees team with their plucky 9 lucky supernovae, everyone would have gone, nah, that's crazy. But very soon, a month or so after their paper came out, the Saul Perlmutter's team with the big telescope and the big number of supernovae came out and confirmed that same result. So we are stuck with it, this crazy phenomenon that there's some additional source of energy in our universe that's gaining, this energy is growing and causing our universe to inflate at an incredibly rapid speed. So mantle handed to the theoretical physicists. Now, this observation has been made. What could it possibly be? And the simplest answer, I want to talk about the physics of nothingness. We're going to do this one. Right. The simplest answer comes from Einstein's field equations. All right. At this point, you're all probably thinking, oh dear, this talk has taken a turn for the worse. Don't worry, you don't need to know what any of those symbols mean. But for those, the small members of the audience who took a general relativity course, give yourself a pat on the back. But for the rest of you, really don't need to know Einstein's field equations. They are the maths of our universe. They describe how things work in our universe. And I quite like it that you can fit it on just one slide. But the terms on the left-hand side are terms that deal with how space-time curves. So, I said, Einstein tells us that mass curves space-time. Well, that's all the stuff on the left-hand side. And the stuff on the right-hand side of the equation is all of the mass and the energy in our universe. Okay, you can read the equations in 2 ways. From left to right, it tells you that the curvature of space and time tells mass and light how to move. So that when I was talking about how that light was bending as it traveled through the universe, that's the curvature of space and time telling mass and light how to move. Or you can read it the other way around, and it's mass and energy tells space and time how to curve. So it's the mass that's curving the whole of space-time. And that's all contained in these equations. Now, zoom in on one particular term, this little beast here. This is known as Einstein's cosmological constant. Now, some of you might have read about this in New Scientist. This is known as Einstein's greatest blunder, because when he was deriving these equations, he put this term in. Or did he not put it in? Yes, no, he put it in. He put it in because mathematically you could do that. So when you're solving these equations, there are lots of integrals. And for those of you who are mathematicians, when you solve an integral, you can always have a constant of integration. That's what this is. It's a mathematical constants of integration. For those of you who don't do maths, don't worry. Basically, all it is this term can be there or not. It's there just for mathematical reasons. Einstein said it was his greatest blunder because without it, the universe expands. But we actually need it now to cause our universe to expand faster and faster and faster. The problem is, I don't like things being there just because maths says it has to be there. Maths is the language of science, but all the other terms in this equation have a fundamental basis. They come from something physical, like mass and energy. This term just comes because you've solved an integral. So what could it be? So at this point, we get to talk about the physics of nothingness, which is nice because we get to have a moment of relaxation. So I want you to imagine that you are in a gorgeous void in one of our universes. Our universe is full of these massive voids where there's absolutely nothing. Okay. So there are no galaxies, there are no stars, there's no gas, there's absolutely nothing. You're in a perfect void, a perfect vacuum. There's nothing there apart from virtual particles. So quantum physicists will tell you there's no such thing as nothing, which is nice. Because when there is a vacuum, virtual particles can pop in and out of existence. And this isn't just quantum physics making things up. This is real. You can measure it in a laboratory. And when you have a fixed vacuum, a fixed volume of vacuum, virtual particles just merrily pop in and out of existence. Great. Now, our universe is expanding. When our universe was created in a big bang, it starts to expand. So that means our vacuum, that void of nothingness that we're sitting in, that vacuum is expanding. And when you've got an expanding vacuum, there's more opportunity for particles to pop into existence than popping out again. And in doing so, they give energy to the system, because when they are created out of the virtual realm, if you like, they give energy to the universe, which causes it to expand, which creates more vacuum, which causes more opportunity for virtual particles to pop into existence, which creates more energy, more vacuum. Oh, we have the solution to dark energy. It's just the physics of nothingness. So that's great. Good. Problem solved. Sadly not. If this mechanism is behind dark energy, you can estimate how much energy is created. And if this is correct, if this idea is correct, then we wouldn't be here to be talking about it, because it would have kicked in so early in the universe that the first stars and galaxies would never have formed, and we wouldn't be here to think about it. So cross that one off the list. What could this dark energy possibly be? There's a long list. So some people say, yeah, it's just the particle. Quantum physicists don't know what they're talking about. It's this. I like this idea. It's just cosmological constant. Done. Other people say, well, what about, is it a new force field? All right, so you often get energy from forces. Imagine you are on your bicycle at the top of a hill. You're going to get a lot of energy as you go down that hill. That's just gravity giving you energy as it pulls you down. So we could have a new force field other than gravity, electromagnetism, and the strong and weak force. Maybe there's a fifth force in our universe that's giving the universe this energy. Crazy ones, colliding brain worlds or multiverses. It could be that there's another universe out there sucking our universe into it. Oh, wonderful, love those sort of ideas. Or maybe, do we need to go beyond Einstein's gravity? Do we need to modify it? Everything I've told you so far, my whole story that I've been telling you this evening, is all based in a framework where Einstein's theory of general relativity explains the universe everywhere, at all points in space and time. So I said at the start, you know, when I was saluting those of you who thought I was maybe making dark matter up, you know, I saluted. Let's check this out. It's not completely mad to start questioning Einstein. There's been an evolution in how we understand gravity. So Newton said that gravity was stuff attracting stuff, and that the gravitational constant was a fundamental constant at all points in space and time. And Einstein said, no, it's not stuff attracts stuff. It's that gravity bends space and time and things roll together. But he said that happens in the same way everywhere across all of space. Could gravity bend space and time differently, maybe? Is the gravitational constant really the same everywhere? These are the questions that we're asking. I haven't managed to find an answer yet. Everything we do, everything we test comes back with Einstein coming up trumps, but there is more data on the horizon. So I'm going to skip a couple of slides because I realize I have been going too slowly. And let me tell you what's on the horizon to wrap up this talk. I am delighted to be a member of the team who is going to be using the Vera Rubin Observatory. This is a big US project, so it's a big telescope, but there is involvement from all across Europe. This is it in the construction phase in August 2018, July 2020. We had to down tools again at the site during the pandemic, so we're about a year behind schedule now, but we will be opening the domes and the telescope to first light next year. Now, what are we going to be doing with this observatory? Well, we are going to be surveying the entire night sky on repeat for 10 years. So we're going to be building up a movie of our universe. With that, we are going to be able to see things that go bang and things that move. So for those of you who are existentially worried about a future impact from a killer asteroid, Vera Rubin Observatory have got you covered. We will be able to map out the majority of asteroids in our solar system to be able to calculate if any of them are going to have a direct collision course with Earth one day. And if there are any, then we can go mobilize Bruce Willis or The Rock to go and get them out of line and make sure they don't obliterate planet Earth. That's not my personal interest in the Rubin Observatory, although I'm pleased that people are worrying about that. With this 10 years of observation of the entire night sky with an 8.4 meter telescope, oh, gorgeous. The camera, by the way, for this telescope is the size of a Fiat Punto. It's massive. It's absolutely gorgeous, this telescope. We are going to create the deepest, widest image of the universe that we've ever seen. So those blobby maps that I've been showing you of dark matter that we've been painstakingly putting together over the last 20 years of my career, we're going to be able to do that across the entire night sky. And what we can do is look at how that dark matter is changing and evolving with time to see what's happening with the dark energy. And we directly test Einstein's theory of general relativity at the same time. Now, astronomers get lots of presents all the time, and it's not just the Vera Rubin Observatory that's coming online soon. We are also going into space. This is your amateur astronomers, so I can say it's 0.4 arc seconds seeing this. This is one of the best nights of observing we had in Chile, but still the typical galaxies that we look at are pretty fuzzy blobs. And when you're trying to look for these small distortions, then it is really good if you can go up into space. These are images from the Hubble Space Telescope, and you can see this exquisite resolution. If you can get above the atmosphere, then your life is so much easier when you're trying to make these observations. So due for launch at the end of 2022, the Euclid satellite. This is a big European Space Agency project with input from NASA as well. I'm super excited to also be part of this team, and actually it's the combination of Euclid and Rubin working together. Again, mapping out the dark matter, seeing how dark energy are changing things that I'm really excited about. And I hope that over the next 10 years, the combination of these two amazing new data sets are going to really give us so much data to understand this mystery of dark energy. I hope by the time we get to the end of it, I will be able to tell my son that the particle physicists have discovered a dark matter particle, and I understand that, and that we've discovered what the origin is of this dark energy. It's widely believed that we're going to need new physics to be able to answer those questions, but I have a nagging feeling in the back of my head that we may end up concluding that we're just in a bit of a weird universe in the multiverse. But there's a whole other talk that I could give the Astronomy Society of Glasgow about the multiverse, so I will save my thoughts on the multiverse for another time when I can hopefully come and meet you all in person. But it's a whole wonderful theoretical world out there that we can actually dive into with observations. Right, I will wrap up. 3 things to take home. We need dark matter. It appears to be surrounding our Milky Way galaxy. If we didn't have it, our Milky Way galaxy, all the stars would fly out into space. They're spinning around too fast. So we need invisible dark matter there. It is our friend. There's this, an evil sibling, dark energy, which appears to be speeding up the expansion of the universe. We don't understand either of these two things. They make up 95% of the universe. And so the major big quest for science at the moment is to understand them. And that's because our final understanding is very likely to involve some brand new physics that will be able to teach our undergraduates a whole revolution in our understanding of the world around us. So thank you very much. There's a book if you want to have if you're super into this, check out this book. It's free to read. I firmly believe that education should be free, so all of my stuff is free to read. Just Google my surname, Heymans, and Dark Universe. And there's also a course on Coursera. They will try to charge you. Just keep clicking the no, I don't want to pay, and you'll get to the free option. It's exactly the same as the paid for option. Don't ask. This is a free course about the science and technology behind astronomical discovery. And week 6, we do the Dark Universe. This is something I co-lecture with Andy Lawrence. So I will stop there. Thank you very much for your attention.
Well, thank you very much, Catherine. That was fascinating and perfectly pitched, I think, and for people who maybe have not come across this stuff before, because as you say, it's some very scary and bewildering physics behind this potentially. On that point, I'll ask a quick question, and then I'll move on to the many questions I'm sure we're going to get. The last time that astronomers and particle physicists had a big disagreement, if I remember correctly, was a solar neutrino problem, where we didn't count the number of solar neutrinos that we ought to have done, given the nuclear reactions that astronomers had modelled in the centre of the sun. I think it's fair to say it's astronomers 1, particle physicists 0 after that. Is that mentioned? Does that ever come up at all? The last time that you had a match?
Yeah, definitely 1-0 for the astronomers. So for those of you who aren't familiar with this story, the nuclear reaction that's happening at the center of our sun is converting hydrogen into helium. And that reaction creates a type of neutrino called the electron neutrino. Now, there are 3 types of neutrinos. There's muon neutrinos and tau neutrinos. And particle physicists said that these 3 things were completely independent, very independent neutrinos. And astronomers did their calculations of exactly how many neutrinos we would expect to detect from the sun, and we detected a third less. Yes, a third less than was predicted. And so the particle physicists said, "Oh, astronomers, you have no idea what is going on in the sun. Go back to your calculations." And we said, "No, this is right." Turns out that neutrinos have a bit of a personality disorder, and in the 8 minutes that it took them to travel from the sun to the Earth, some of them changed into muon neutrinos and some of them changed into tau neutrinos, and they weren't detectable by the particle physics experiment. So 1-0 to the astronomers. This is now it's astronomers against quantum physicists. Yeah, it's a hard one. So the quantum physicists say they can work out how to make this effect be 0 or a really big number. Classic quantum physics is 0 or big, but they can't work out how to make this effect give you this kind of low level dark energy that we're seeing. So yeah, it's a tricky one. It bugs me. At least with dark matter, there are good ideas about what it should be. So the particle physicists have got this idea that there could be a sort of mirror images of the particles that we have, that we know and love in the standard model, and that's called the supersymmetric theory, and it's built around string theory. At least there's a sort of a compelling argument there. Whereas with dark energy, you start reaching for the multiverse and colliding brain worlds, which are brilliant and awesome, but quite far out. So that is a big problem, that we don't really understand what's going on. So really our best guess is that it's Einstein's cosmological constant. But that was the bit of my talk actually that I skipped over. Even that's looking troubling right now, because our data is actually saying that's almost ruled out now. So interesting times.
Okay, thank you. So I've got some questions in the Zoom chat. We'll also have questions coming in from the YouTube chat. So I'll take them in the order that they come in. So the first question was from Julian. Julian, would you like to ask it in person, just so Catherine gets to see some faces rather than disembodied text?
Hi, Julian. You're totally muted.
Sorry, Julian, you should be able to unmute yourself now.
Sorry, right, okay, thanks. Catherine, thank you, that was great, thank you very much. How will Lux Zeppelin differentiate a potential dark matter particle from other weakly interacting or rarely interacting particles, such as neutrinos? when you don't have a theoretical model for what the dark matter particle might be, please?
An excellent question, Julian. For those of you who didn't understand the question, Julian's asking about this big underground vat of xenon that the particle physicists are using to try and capture one of these dark matter particles. And the idea is the dark matter particle comes in, crashes into the xenon, creates a little bit of energy, and they detect it. What Julian's saying is, but there are other particles around. So we just talked about these neutrinos that are being produced from our sun. Ooh, can I remember? There are, I think, can't remember, it's 10 or 100. I think it's 10 million neutrinos fly through your thumbnail a second. Is that right? It's one of the questions I set my first year undergraduates. I can't remember now. Anyway, a lot. There are a lot of neutrinos as well. So Julian, that's why they bury themselves supremely deep underground. To get rid of most of the particles. The neutrinos still fly through there, and they call this is going to be the kind of the limiting factor of this approach. So if they get the entire world's supply of liquid xenon together, so that's 10 tons, then they will be if the dark matter particle is slightly more massive than a neutrino, and bear in mind that particle physicists think that neutrinos don't weigh anything at the moment. But yeah, a little bit of mass for the neutrino. With 10 tons, that's where they'll hit the limit where they won't be able to distinguish between neutrinos and dark matter particles. So the hope is that the dark matter particle is slightly heavier than the neutrino, otherwise this method isn't going to work. But I say it's worth trying. Let's assemble the world's entire supply of xenon and bury it in Yorkshire.
Thank you, fingers crossed.
So next question I've got here is from John I. If dark matter exists and particles of it are flying around, why don't we notice the gravitational effect here on Earth?
Yeah, no, that's an absolutely brilliant question. So it's because Earth is a really weird place in the universe. So most of the universe is very low density in the type of stuff that we're made up of. So if you take a mug full of the universe, for most of it, it's mainly dark matter. But because we are in our Milky Way galaxy, where the ratio of the stuff that we're made up of to dark matter is very different. So there's still lots and lots of dark matter around us. It's still the dominant gravitational force, but most of that, but the dark matter is kind of spread out much larger. So if you imagine the big clump of dark matter that's around our galaxy, the light that we can actually see from it is just kind of like a tiny dot in the middle of it. So the dark matter is just much, much bigger, and just we're at the center where there's a lot of the baryons that we're made up of. So people are trying to detect the dark matter flow though. So there are experiments, space-based experiments that they're thinking about. There's a Chinese one at the moment as well called, what's it, Dampe. Is it Dampe? Oh, I can't remember the name of it. So that's looking at cosmic rays, but at the same time, it should be able to detect the flow of dark matter. So as the sun moves around in the galaxy, the idea is it should be able to detect a flow of dark matter with enough data.
Thank you. So the next question I've got here is from Sean M. And this is a question that I think would keep a physicist up at night. Is there any possibility that the laws of physics are not constant over the very long periods of time involved?
Yeah, excellent question. So that's one of the things we're testing, right? So Einstein's theory of general relativity says that the laws of gravity do not change no matter where you are in the universe at any point in space or time. General relativity is tested. It is the best tested theory on planet Earth. You know, your sat nav would not work if we didn't understand general relativity. It is phenomenally brilliant at predicting things in our solar system. But as I was just saying, we're in a bit of a rare place in the universe. Most of our universe are these giant empty voids. Could gravity work differently there? What's to say it doesn't change and evolve with time? So the reason why Einstein says it doesn't change and evolve with time is because of the sort of the fundamental theory that goes into it. But this is what we can test, and this is one of the brilliant things about astronomy is you get these gorgeous fundamental theoretical physics theories, and you get to build really big tech and big kit to go out and test them. And we are now pushing back. So with the Vera Rubin Observatory, we'll be looking back. The galaxies that we'll be looking at are 12 billion light years away, so we can really see how the universe is evolving and changing with time. Does light travel at different speeds? The gravitational wave events put really tight limits on that, so we think light really is constant throughout the universe, but maybe gravity changes in different environments. These are things that we can actually test and are testing.
Okay, thank you. So next, a question from Stephen Schreier. What effect might constellations of low Earth orbiting satellites have on future observations by the Vera Rubin telescope? Is the regulation of the satellite launches needed?
This is a brilliant question. Oh, it just breaks my heart what's going on. SpaceX. I loathe it. It's bad. It's bad. So for those of you, I'm sure you're all aware, you're all amateur astronomers, you've had all of your images ruined by satellites going past. If SpaceX gets their way, then we will have to trash about 30% of our data. So we could just take another 3 years of observations. In the grand scheme of things, okay. Could do that. What's most damaging for astronomers is the radio astronomy community. So we've got the Square Kilometre Array coming up soon. There's going to be an absolutely fantastic facility, one in Australia and one in South Africa. For us at the Rubin Observatory, provided we know when things are coming over, and in fairness to Elon Musk, he is doing his best to put coatings on things, and he is trying. So if we have all that information, we can try and not look where these satellites are coming over. But yeah, the predictions at the moment is we'd have to trash about 30% of our data. But the SKA would lose about 60 to 70% of their data. So that's really problematic. I've just seen something from Alistair on the chat. Ironic that SpaceX is one of the best ways to get internet to remote locations. You see, I fell for that too, Alistair, because I was like, but I really want people in Africa to have access to the internet. I genuinely do. It's a game changer having access to the internet. It's very actually the ground tech to get your internet working. It's very expensive, the satellites that you have to get. So it's not really going to be a leveling up for the developing countries to have this unless they change their model. So yes, I am not a fan of the mega constellations. There is lots of discussions going on though. So I don't know if you've invited Andy Lawrence to come and talk to you yet, but he is one of the leading people in the UK, and across internationally, the astronomers are getting together to try and work out if there is an alternative way to do things. So cross your fingers this doesn't happen, but this is happening now. It's in the next 5 years, it could all go really horribly wrong. And once they're up, they're up.
Yeah, yes, a bit of a worry. Now, I imagine David is emailing Andy Lawrence as we speak. But he's disappeared. So David actually asked the next question. David, would you like to ask the question yourself?
Catherine, hello. That was a great talk. Absolutely.
Thanks, David.
Yeah, my question is, what about evidence that matter particles can react weakly with the weak energy bosons? And is there evidence that they might interact with other particles?
Mm-hmm. Okay, so for those of you who didn't understand David's question, he was asking about what we call the WIMP scenario, because physicists love rubbish acronyms. So the WIMP scenario for dark matter stands for weakly interacting matter particle. This is the best guess of what the dark matter particle is, and it means that it interacts through the weak force. So we've got the electromagnetic, gravity, and the strong and weak force. And the strong and weak force are sort of forces that only work kind of within the nucleus. So the idea is that these dark matter particles interact through the weak force, and that's how they can detect them with these xenon detectors. Now, David, your question was, what's the motivation behind that? So, I mean, it's come out of string theory that this is what these supersymmetric particles would interact through the weak force. The fact that they haven't created one of these particles at CERN yet is a problem. So the theoretical predictions were that they should have discovered the lightest supersymmetric particle already at CERN. It wasn't supposed to just find the Higgs boson. I mean, fantastic, it did find the Higgs boson, but that was just supposed to be the start. Then there was supposed to be lots of these supersymmetric particles coming out that they haven't seen. So let's see what happens when they put on their new high energy beam. That's going to be really interesting to see what they find there. But I think I saw it in the chat as well, somebody mentioned axions. So this is another type of particle that would behave like dark matter. They interact differently, not just through the weak force. What's really interesting about axions is that they can also behave like a force field. So, I was saying one idea for dark energy is that there could be a fifth force field that's giving energy to the system, just like gravity gives you kinetic energy as you roll down the hill on your bike. So axions, if they are massive, they behave like dark matter, and if they're low mass, they behave like a force field that could give you dark energy. So people getting progressively interested in axions. And the particle physicists are being very clever, and they're designing these xenon experiments to also have some sensitivity to these axion type theories. So that's a really new, interesting area that's being developed, mainly because CERN hasn't found these yet. I mean, they're really worried.
Okay, thank you. So our next is from Roy Bryce. Roy, I see you're on video. Would you like to ask the question yourself? Oh, no, it's turned off. Oh,
what I was wondering is, I saw something on the net recently about we were already needing extra radio telescopes to try and capture all the data that's coming in from various space probes. So you were saying you've got the Euclid's satellite going up plus the new ground-based telescope. Do you already have computing equipment available to process all this huge amount of extra data, or is that going to be a problem?
No, that's a really, really good question. So the Vera Rubin Observatory is going to be creating 20 terabytes of data per night. So it's got a 3.2 gigapixel camera. So that's a lot. It's something, I mean, I joke about my US cousins, but they're good at big. They are really good at big. And they've been preparing for this for a long time. And working with Google as well. So I've forgotten the name of the second Google. Anyway, there's a lot of money that's been invested in the Rubin Observatory from Google, actually, because they're really interested in working with us. How do you deal with this huge amount of data? So it's not all solved yet. So one of the big issues is, it's going to be in a very remote site in Chile. And so how do you, Chile just doesn't have the infrastructure to get that data out. So they're building on the site, they're building a big data processing centre there to just get the raw basic level data processing done. And then that data is being distributed to 3 different centres. It's going to France, it's going to America, and I'm delighted to say the UK is also going to be one of the data access centres, which is, thank you very much, UK government, for funding us for that. So we've got a big grant from the Science and Technology Facilities Council for the UK to play a major part in that data access. Mainly because it's as you're saying, it's really interesting. How do we deal with this sort of data? And that's something that's going to be down the line a problem for normal people in business and industry. So again, sort of astronomy is kind of really paving the way here. How do we deal with huge quantities of data? How do we mine that data to extract the information that we want from it without losing anything along the way?
Okay, thank you. So a question from YouTube: is dark matter inside stars and planets, or is it all external to normal matter?
So because it doesn't interact with the stuff that stars and planets are made up of, it kind of doesn't get kind of caught in it, if you like. It's sort of so it's just kind of that's a good way of describing it. I kind of like to think of dark matter as just kind of like little ants crawling around, like completely irrelevant to what's going on around it, right? So just imagine these dark matter particles, they're just tiny. They don't even, very occasionally they like actually collide with another particle, but otherwise they're just so small, they're just zipping past and zipping through. So yes, there's dark matter passing through stars and planets, but it doesn't sort of get hot, it doesn't get sort of wedged there just because the gravity of a star and a planet isn't very strong. I hope that answers that question.
Okay, thank you. Next question is from Craig McNay. Craig, do you want to reveal yourself and ask it yourself? I'll take that as a no. The question was, to split space from time, does this give us hope for a time machine as Jules Verne imagined?
Oh, wouldn't that be great? One of the fun things I do is I did a Scotland in Space. It was a collaboration between scientists and science fiction writers. And the science fiction writer that I was working with, he said, I really want to do time travel. And I was like, well, if you want to do time travel, we need to travel faster than light, and that's not possible. He's like, but I really want to do time travel. How could we do it? Come on, there must be a way. So yeah, we'd have to break Einstein's theory of general relativity. So actually for that story, we thought about sort of going back to the birth of the universe. So there's a period in the very early universe, 10 to the minus 30 seconds after the Big Bang. So basically just after the Big Bang, where the universe experiences this really rapid period of inflation. And at that point, it's expanding. It's so hot, it's so dense, the Einstein's theory of general relativity doesn't apply anymore. And you essentially get a faster than light expansion. It's not really faster than light because there's no distances at that time. Anyway, it's like a very rapid, instantaneous expansion. And so we called this the inflation drive, and we used that to write our story about traveling faster than light and doing time travel. It wouldn't be great to do time travel. I kind of think of astronomers, we kind of are doing time travel. Like every time we look out in our telescopes, we are time traveling back in time. So we already kind of have mastered at least one direction in the time travel, but it's the other direction that might be fun to go in as well.
Right, so here's an interesting question from Ian. If your four-year-old thinks you don't know what you're talking about, what are his views and opinions on this topic now that he is 12?
Yeah, I think it's just all been confirmed. You should have heard them when I came home. I said, oh, you'll never guess what? I'm the Astronomer Royal for Scotland. They're like, sure, right, I'm hungry, give me dinner. There's no respect in this household.
Yep, I know the feeling. So
I'm just a mum to my children. I think as all parents are, you're nothing special.
Oh, I'm not so sure about that. So Stephen Schreier again from I think from YouTube. Could axions be a form of dark matter?
Yes, we talked about axions. Yes, so yes, they could be a form of dark matter. I'm getting increasingly excited about axions, Stephen, just because they have this capability to also explain dark energy. So that's yeah, getting interesting.
Yassim asks, do our own bodies have a layer of dark matter around them?
Not a sort of a stationary one. So you probably want to imagine, because the sun is, well, because the Earth is going around the sun and the sun is moving around in the galaxy, there's kind of like a flow of dark matter particles going past us just because we're moving through it. So it and we don't have enough gravity to attract it towards us. So we're just kind of going through this kind of sea of dark matter particles, but because they're so small, we don't interact with them. So let me give you an example, Yassim. So if you focus on the end, on the very tip of your nose for just 5 seconds, depending on how massive the dark matter particle is, there's at least 1 million dark matter particles that will have flown through your nose during that time. Could be up to 1 billion, could be even more, but the minimum is 1 million going through the tip of your nose every few seconds. So that's just how many, that this sort of the sea that we are moving through as the sun goes around in the Milky Way galaxy, and indeed as the Earth goes around the sun.
Robert has a question. Robert is here. Robert, would you like to ask your question?
No, Robert does not.
Sorry, Robert, try now.
You hear me now, right?
Yeah, hello.
Right, hi, Kathleen. First of all, congratulations on becoming our new Astronomer Royal. It's absolutely fascinating. Right?
Oh, thank you
Fantastic,
very much.
I should say. Right. I'm really excited about the James Webb Space Telescope. We've finally got a launch date, the 18th of December. We're all getting a new telescope for Christmas. Hopefully, the rocket doesn't mess up and that mirror unfolds. So my question is, can that be used to help about dark matter and dark energy?
Yeah, no, that's an excellent question. You're completely right. Astronomers are getting a brand new telescope for Christmas. So all astronomers, professional and amateur, have to behave themselves between now and Christmas. Otherwise, we won't get our presents. So everyone has to be very good and cross their fingers that the launch goes off without hitch on the 18th of December. For those of you who aren't following JWST, it has got a long and tortuous route before we're going to actually know if it's working. It's going to take about 3 months before it's got to the L2 orbit where it's going to, the solar panels have unfurled and the telescope has unfurled as well. That's going to be a very slow and arduous process.
I've switched video off, thank you. She's finished, it's in the...
The question was, can this tell us anything about dark matter? So not so much. So the type of science that I do, we need big surveys because we're looking on the really, really large scales of the universe, and JWST is focused on quite a small, narrow vision. So what JWST is going to be doing, the things that I'm most excited about is going to see the first stars and galaxies ever formed in our universe, because it's looking in the infrared light. So it will be able to go back right to sort of 13.5 billion years where we expect those first stars and galaxies to form. That's number one super exciting thing. The second most exciting thing I'm interested in is it's going to be looking at exoplanets going around other stars. So it should be able to look and map the weather. It's going to map the weather on other planets in other solar systems and look at the different chemical compositions to look for signs of life. You know, these are awesome things, but they're kind of just small views. So it's not the sort of the big sky surveys that we need to be able to understand the cosmology of the universe, but looking more at detailed at sort of individual objects. It's going to be proper awesome.
Okay, thank you. David, you have another question.
Catherine, it's me again. Do you believe that massive stars powered by mutual dark matter particle destruction existed in the early universe?
All right, so massive stars and dark, right. Are you talking about primordial black holes, maybe?
It was just, it was a documentary I seen maybe a year or two ago, and this was something that was speculated about, that stars that huge that existed early.
Okay, so yeah, when for people who didn't understand David's question, so when a star dies in a supernova explosion, a black hole is left, and we know that there are supermassive black holes at the center of each and every galaxy. And there have been signs recently where you expect little black holes to kind of accrete down to the middle, and there's some evidence that there are sort of hundreds of little black holes surrounding the big black hole at the center. Very exciting stuff. In the early universe, the first stars that formed will be very, very massive. So they would have all sort of had these supernova explosions creating these black holes. And we call these primordial black holes because they're the sort of black holes left over from the very first stars. And the question is, could there be enough of them to be responsible for dark matter? Now, because these are sort of compact objects, when they move in front of us, they change the light from background galaxies. So this is something called microlensing that people have been looking for, and they've set a limit on the size that these primordial black holes can be. So they can't rule them out, but they have to be smaller than the size of the moon. So there could be loads of like moon-like primordial black holes around, but it puts quite a tight limit on them. But you can't rule them out completely yet.
Okay, so we've got 3 questions remaining. I think we'll take these last 3 questions and then we'll wrap it up, because we've been talking for well over an hour.
I could talk for Britain, honestly.
Okay, so it's Yasim on YouTube again. Couldn't you travel to the future by time dilation? It's technically time travel, right?
What, by just slowing time down where you are? I mean, there's the sort of the paradox of you have 2 twins, don't you? And you send one up out of the, because when you change your gravitational field, your time changes. So if you have 2 twins and you send one out of the gravitational field, they'll age differently from the twin on the ground. Is it time travel? Time is relative, and that is why Einstein's theory has got the word relativity in it. That's my considered answer to that question.
Another one from YouTube, Paul Kent says, hello, do discrepancies in the value of the Hubble constant, Planck data versus type 1a supernova, suggest some new physics or something fundamental we don't understand?
Yeah, thank you so much, Paul, for asking that question. Those were the slides that I skipped over because I realised I'd been talking too slowly. So for people who don't know what Paul's talking about now, things are even more mysterious than we thought. So this idea of the cosmological constant, which seemed to explain a lot of our observations, actually doesn't anymore. So people are finding that the universe is expanding faster than we expected it to be with this cosmological constant model. And my data, the dark matter data that I've been showing you, is much more smooth than we would expect from a cosmological constant theory. And these 2 things go hand in hand. If you're reading New Scientist, this is called tension cosmology at the moment. It's called tension because people like me are in tension with the big cats of cosmology who made measurements of the cosmic microwave background, and we're finding different things. So Paul, jury's still out on whether this is evidence for new physics or whether someone hasn't quite done their data reduction right. I personally know I've done my data reduction perfectly. I feel very confident about this now after 20 years of doing it, and not feeling so confident along the way. We've done a lot of work, and I feel very confident. And Adam Rees, who was the gentleman in the photograph I showed you earlier with the interesting body language, he's been making these measurements as well, and also finds something interesting. So yeah, it's going to be really exciting, Paul, to see what we find with the next generation telescopes, because if we carry on finding what we're finding right now, then our universe maybe needs even a 3rd dark ingredient, or something really strange is going on. So yeah, it's genuinely exciting times. I hope I haven't done my data. No, I haven't. I keep thinking it's me who's done something wrong, but I haven't really. We've done a really careful job this time.
Okay, and our final question is more of a topical one than about your talk specifically, but it was mentioned earlier before we started the formal lecture. Any comments about the large object that collided with Jupiter on Monday?
Oh yes, that was very exciting, wasn't it? I'm on Twitter now because somebody said if you're the Astronomer Royal for Scotland, you have to go on Twitter. And I saw on Twitter, did anyone see that flash on Jupiter? And somebody was like, oh yes, here's my. I love all of the amateur astronomers on YouTube, on Twitter. They're fantastic. Just seeing all this stuff. So yeah, no, what can it be? There's all sorts of stuff flying around in our solar system all the time. You know, you kind of think of Earth as this wonderfully safe place. But you know, things are crashing around all the time. Now Jupiter's in the hot seats, if you like. You know, it's the biggest thing out there apart from the sun. So if things are going to hit, Jupiter has a hard time. So probably just another asteroid, but no, really interesting to see what that is, and I think also to see what's happened afterwards. So hopefully some Ceres telescopes are going to have a look at that. But that's, you know, one of the reasons why the Vera Rubin Observatory was actually funded. You know, the US are really good. They said we want something to understand dark energy, and they said no, and they went back and said we want something to track all the killer asteroids. They said here's the money, so build something good. So yeah, it's going to be really interesting to see how the map of our solar system looks when we get this really deep data to see all of the different transits of the asteroids in our solar system.
Okay, thanks very much. And can I ask you all to thank our speaker for a fantastic talk and taking time to answer all those questions.
Thanks very much, everyone. And when you guys are back in person, I'm just a 40-minute train ride away. So please invite me through because I need your help. I am the Astronomer Royal for Scotland, but I am a totally rubbish amateur astronomer. And you guys know what you're doing. So come, invite me over when you're back in person and teach me.
Yep, we will do. We might even invite you to our observatory when we finally get it built.
I would love to come and see it. Yeah. Thank you so much.
Thank you very much again.